My energy video is really rushed, so I'm really sorry about that. I'll maybe make a new one because I know energy is important. But for the momentum video, I've actually like taken notes down and I've thought this through about how I'm gonna explain it. So hopefully it's not rushed. And I'm gonna, instead of like sort of, I think what I was trying to do is I think I was trying to go through like every SCP 4, 5, like every SCP 4 thing, every SCP 5 thing, every SCP 6 thing. But I think what I'm gonna do instead is I'm gonna actually go over every concept of like momentum, like key concepts, and then explain like how SCP 4, 5, 6 connects back to that. I think that might be better. But yeah, I'm sorry about the lame energy video. I'm gonna try to do a better job with momentum. Might as well just get started with momentum. And with the conceptual background, like, you know, like if you had to, you know, define like what momentum is, it's kind of hard to define, but I think it's something that we actually have a grasp on, like a pretty well like understanding of what momentum is, right? It's the amount of like oomph an object has. Like if there was a truck versus a car that was going at the same speed towards you, you can imagine that the truck would probably hurt more, right? It would have, you know, more of that punch, more oomph, I guess, if you want to call it like that. So momentum is this idea of mass in motion, right? How much momentum an object has. I think it's pretty intuitive to kind of understand. The equation for momentum is P is equal to mv. So if we think about our example before, right? If you have a car with, I don't know, maybe a certain mass, and then you have a much more massive, you know, truck, you know, coming at you, you can imagine, even at the same speed, the truck is going to have much more momentum. And let's say that, you know, this had 2 times more mass, right? If they want to, in order to have the same momentum, 2 times the mass, this would have to be traveling at 1/2 the velocity, right? So even if this is 2 times the mass, it can have the same momentum as a car if it's going at 1/2 the velocity. So momentum is kind of the product of those 2 things. That's really kind of momentum. I think conceptually it's not something terribly hard to understand. I think momentum, we see that in our everyday sort of life. If you're moving faster, or if you're moving really fast, you know, and if you, you know, bump into someone, it's just going to sort of hurt more because you have more momentum. So momentum's pretty cool. What the AP test is worried about is really change in momentum. Change in momentum is one of the kind of a big key concept. So momentum, right? If an object has no net force on it, it's going to have a constant velocity. We studied this extensively in Unit 2. No net force, constant velocity. So if you think about an ice cube, right, on friction, right, it's going to be going at that constant velocity, so it's going to have constant momentum, right? In order to change that momentum, there's a couple things you could do. First thing, you could speed it up, right? You can make it go way faster. It's going to have way more momentum. You can also make it go slower, and that's one way you can change momentum. And now a second way you can change momentum is changing its direction. So it can go at the same speed, but right, if you had a top view, if you made it go in a circle, it would have a constantly changing momentum because the velocity is constantly changing in terms of its direction. So changing its speed and changing its direction in both cases requires a force. Now, this is kind of different. We just kind of did, not just, but with Unit 7, right, we learned, I don't want to go into too much, but right, L equals I omega. So what can happen is that your omega can increase, and then for this to stay constant, your I can decrease. For linear momentum, I made a mark on my wall. Oh well. For linear momentum, mass cannot change. All right, this m is fixed, no matter like for an object, its m is fixed, right? If I chop off my arm and I throw it, my mass did not decrease. Really, it's 2 separate systems. Everything but my arm, and then the system of just my arm, right? And when I throw it, that, you know, system experiences a net force and all that, but I can never like remove this out of my own system, right? The Krishna system will always be the whole thing, and when I throw my arm, the mass is still the same because the Krishna system hasn't changed, but like individually, like I can't take my arm out of my system and say my whole overall mass is decreased. It hasn't. My arm still contributes to my overall mass. So, like for a train and passengers jumping off, you can't say the mass decreased because the system was the train, and then afterwards the system is like maybe the system is train and passengers, and then afterwards it's still train and passengers. It's just the passengers are off the train. So that's a common thing that like with angular momentum we're kind of used to, like, okay, your rotational inertia can change. Remember, mass is fixed for a system. So just be careful about that, but I think other than that, really, I think we've kind of figured out that an F net will cause a change in momentum, right? There's some sort of relationship there. If I have a net force, there's going to be a change in momentum. And specifically, the equation, so I'll get into the equation now. Keep dropping shit and it's kind of annoying, but the equation for momentum is that F net times time is going to cause a change in momentum. So if I apply a net force for a certain amount of time, it's going to cause a change in momentum. And let's actually say F net times time. A change in momentum is just your change in mass times velocity, right? Like your change, like if I just substitute that in, your mass is fixed, so it's just mass times change in velocity. But this is pretty cool because now, if you give me a force, how long you apply it for, and then the mass, I can just figure out how the change in, what's the change in velocity, right? If I change this even further, F net times time equals mass V final, or yeah, we could do mass, right? V final minus mass V initial, or mass times V final minus V initial, if you just, factor out the m. So, yeah, there you go. That's kind of how you that's kind of the equation for change in momentum. And if you're curious, like, why is it F net times time? Well, remember, acceleration, the kinematic, so let's do the kinematics equation. Your change in velocity is going to equal the acceleration you experience times time. Well, I want force in there somewhere, right? I want to think about how does force cause a change in momentum, which causes a change in velocity. I want to see how force changes that. What I can do is I can just, let me make this a bit neater. With that change in V equals acceleration times time, I can tack on, like I can multiply this side by m, and then I have to multiply this side by m, right? So I'm just showing you where the equation comes from. M times change in V is equal to your change in momentum, and then mass times acceleration times time. Mass times acceleration, that quantity is just your F net. That's the F net you experience. So we can say mass times acceleration times time is the same as just F net times time. That's kind of where the equation comes from. And we're gonna, that's mathematically where it comes from, and we're gonna make it make sense, kind of right now, and talk about where do we use this equation and stuff. And one of the first things we kind of learned is how do we try to maximize how fast something is moving. So, let's say you're playing baseball, you're playing badminton, whatever you're playing, you want to make that birdie or baseball, whatever you want it to go as fast as possible. And you want to obviously, right, when you're swinging or when you're like driving it, you want to, is that the word? I don't know. You want to apply force, and you want to make it go as fast as possible. So let's take a look at F net times time equals mass times change in velocity. So I need to make it go as fast as possible. I can't change the mass, right? The birdie's gonna have whatever mass it has. I don't really have control over that. And the goal is that we want to maximize, that change in velocity. So we have two things we can control. We can just hit super hard, right? We can hit it as hard as we possibly can. But people like me, we're not really strong. Our other option is increase how long we apply the force for. If we, let me draw the baseball, right? If we have, I don't know how these will look. If I have my baseball, right, and then the ball is coming in with the velocity of v. If I'm going to make contact with that baseball as long as possible and just sort of follow through, try to make as long as contact as possible, that force is going to be applied for a really long time. It's going to have a larger change in velocity, right? It's going to be moving much faster if I follow through, and that's why, like, you know, a lot of, when you learn sports at a young age, that's kind of what you learn. Try to maximize, like, try to follow. Oh my God, everything's just dropping. You try to maximize the amount of time so that it's going as fast as possible. So that's kind of how you can sort of take advantage of the fact that F net times time equals m times change in v. You can take advantage of that, try to increase time as well as force to get the fastest possible ball. And remember, right, change in v is a good thing to bring up direction. Direction is important. Our ball is going to have, if it's coming this way, if we say this way is negative, or let's say this way is positive, and then this way is negative, right? Its negative, its final velocity will be negative because we're changing direction. So, and then we're doing minus initial velocity. And let's say we want this, like the v final, like the speed is the same, that would be negative 2 times m times v, right? Because you're changing direction. We're going to talk about changing direction more, but just as a reminder, right? Direction matters for momentum. It is a vector. It has a direction. Okay, so that's one example where we can use, you know, the law. I guess the law of the momentum impulse theory. Oh, I didn't even talk about that. This is impulse. Change in momentum is impulse. That's just a fancy word. You'll see it like J. Maybe, because this is also like joule, so maybe you'll see this as J for impulse, but yes, change in momentum is impulse. It is called the impulse momentum theorem. It's just saying that forces cause change in momentum. That's really all it's saying. So, one way we can cleverly use that is if we're trying to stop something. So maybe you're jumping, right? Maybe you're jumping off a tree. I used to climb a lot of those as a kid, and I'm on the ground, and I'm like gonna fall. And I'm going to stop myself, right? I'm going to have a certain V initial, and then to stop myself, my V final needs to be 0. So just to get a mathematical sense of what's going on, let's just take this equation. F net times time is going to equal m, and then we're going to use the m times V final minus V initial, just change in velocity. So V final is 0, and then minus V initial. And then F net times time is going to equal negative, it's going to equal negative mv initial. Alright, so we got to stop ourselves. We don't have control of our mass, right? We don't have control of our initial velocity. Like, however fast we're moving when we hit the ground, like that's not up, like that's fixed, right? That's just how fast we're going to be moving, right? And you can get fancy with energy and figure that out. But the point is, this whole term is, let me get my other marker. I forgot my entire marker set dropped. This term right here is fixed. It's a constant. No matter what, I need to stop I need to stop myself, right? And the impulse required is going to be equal to negative mv in negative m times v initial, no matter what. That's fixed. That's the amount of impulse I need to stop myself from falling, right? And when I hit the ground, that's the amount of impulse needed. So I have two options. I mean, if the time is short, so let's do the classic sort of thing. I can either have a really high, I'm gonna do green, really high force, right? A really high F net by my feet and the ground and stuff. Not by my feet. I can't apply force on myself. By the ground, right? The ground can apply a really high net force for a small amount of time, right? I can do that. Or what I can do is if I increase the time, because this is fixed, because I need less, or because I need the same amount of impulse no matter what, increasing the time allows me to decrease the actual force. It'll hurt less. And I mean, we've been there, right? If you ever climbed up a tree and you're like ready to fall down, your friends at the bottom are always telling you, bend your knees, right? Bend your knees when you land, because then you're in, like, as you sort of bend your knees, you're increasing the time that it takes, right? Instead of keeping your knees stiff and then just breaking them, if you bend, you can kind of like increase the time the force is exerted. So, a couple of things to kind of keep in mind with this. The reason that high time leads to low force is because this is fixed, right? The amount of impulse we need to stop ourselves, no matter what, is just negative m times v initial. Like, that's a fixed amount of impulse. Like high time here does not mean low force here, because this term is not fixed. Like, the whole thing with the baseball is we're trying to increase this term. So because of that, yeah, of course we want to increase time, and of course we want to increase force. In the case of stopping ourselves, this is a very important thing. This is, the final velocity is always going to be 0 because we're stopping ourselves, and then the v initial is just going to be our like speed before impact. Like, we don't have control over that. Therefore, what we do have control over is the time and the force. So high time will lead to low force, right, mathematically, because this is fixed. And another thing, right, a lot of people are like, okay, time, and I'll get this with the egg drop. The egg drop is going to kind of combine both these ideas. Sometimes we're like, oh, well, what's the time? Like, what is it? The time it takes to fall? Is it the time like this, that? It's only the time of contact. And the reason for that is because this equation is saying, like, when the time the force is exerted. The only time that the force can be exerted is when you're in contact with the ground. That's the time we're looking at. Like, how much time are you spent on the ground? Now, obviously, this kind of gets a little confusing because for something like dropping, right, you're always kind of on the ground. Like, when you stop falling, you're still on the ground, so your time will just go on forever. It's the time the force is exerted. So, right, as you're falling, you need to so, okay, wait, this is going to kind of get a little complicated, but I think you guys can handle it. I know I can. You're going this way, you're falling down, and you want to slow down. So in order to slow down, you need an acceleration upwards, okay? So if you want an acceleration upwards, you need an upward force in order to stop yourself from going down more. So on contact, right as you hit the ground, the Fn is bigger than the Fg. But then obviously, right, the Fn is going to be bigger. When you stop, right, when you're at rest, right, when you're finally on the ground and you're not like falling anymore, then the Fn is going to be equal, right? After you are in like sort of equilibrium, you're not falling anymore, right? When you hit contact and you're like not, moving down, right, it's going to be equal. So the time is when the Fn is really big to the time when you're not accelerating, essentially. That's the time. And I mean, it's not like you're gonna have to measure that like on your AP test. Like they'll tell you like, oh, he exerted, like, the ground exerted a force for like 2 seconds, right? That, just use that time they give you. That's usually gonna be a safe bet. They're not gonna, it'd be really hard or maybe they'll ask you for the time. Like, how long was Fn bigger than Fg? It's for the time it was. Like, you did this divided by the F net they give you and stuff like that, right? So just keeping that stuff in mind. So I know I was kind of yapping there. These are kind of, I wanted to bring up all these key concepts. 18 minutes. So I don't know if I'm gonna make a part 2 on this. Okay, I'm just gonna quickly go over now. The rest of the stuff is no, it's not. It's fine. I'll go over it. So couple things to keep in mind. Some SCP-4 stuff that kind of involves with this. If you had a force versus time graph, the area under the curve is the impulse, right? So let's take a case of like a low time and a high force versus a high time but a low force, right? So the force is exerted really high and then it becomes 0, and then the force becomes really kind of lower and then becomes 0. The area under those two things are the same. And that makes sense, because this is a fixed number. Like, the impulse is going to be the same in both cases, right? The impulse is going to be the same. So the area under the curve is going to be the same. A common misconception is that if I bend my knees, the impulse is lower, the force is lower, but the total impulse has to be the same, because mathematically 0 and then v initial, so it has to be the same no matter what. So the area under the curve there is the is your impulse, and then so then you might have a momentum versus time graph, and we'll touch more on those. Your momentum versus time graph, the slope is your force. And the reason for that is actually, if you rearrange this, your slope is going to be your change in p over your time. So if you actually take this equation, change in p over time is just your f net. And that's actually how I'm pretty sure Newton discovered his second law of motion. Like, he did it in terms of conservation of momentum, which we actually have to talk about right now. So, I'll talk about bouncing later. Okay, collisions. Let's just talk about collisions. So, collisions are kind of a big deal in this unit, and they tie back to energy as well. Collisions are all about conservation of momentum. We're going to talk about what that means. If two things are colliding, maybe they're cars, or maybe they're like billiard balls or whatever. Two things are colliding. They're both exerting forces on each other, and we know that as they collide, the forces they exert on one another are equal and opposite. This car exerts an equal force. This is A and this is B. FA, the force exerted by A, is the same as FB, the force exerted by B. So, now, let's say they sort of come, they crash, and they come to a stop or something, or maybe they crash, and let's just say, whatever, let's say for right now, they both are going to obviously experience an impulse. That's kind of what I'm getting at. They're both going to experience an impulse. Forces cause impulse, so they're going to experience a change in momentum. Now, this car is going to experience a force, FB, right, for a certain amount of time. Maybe that's like a millisecond, or like 2 seconds, because that's fast of a collision. So FB times t is going to equal its change in momentum, the car B's impulse, or this is car A. And then car B is also going to have, a change in momentum, which is going to be FB times time. And this is where Newton's third law, right? These are equal and opposite. That's where this comes into play. If FA, let's say FA, right, is positive, then FB is just equal to negative FA. Right? In terms of direction, it's in the opposite direction. But then FA, it still has the same size of a force, same magnitude, equal and opposite. So, the time, and this is kind of the connecting part, the time of the collision will also be the same. Like, the contact time is the same. So, in theory, and I actually have to fact check that, I don't 100% know that. It makes sense that it would be. I'll get back. My point is what I'm trying to say is, if time and the force are the same, they have equal and opposite changes in momentum. So, what that means is, if you took the momentum, so let's say before the collision, so before they collided, this car is going to have a certain amount of momentum. I'm going to put an arrow, because it's a vector, just to indicate direction. I'm just saying it has direction. I'm just not writing plus or minus. Right? I got dust. I shouldn't clean with my hand. So P, momentum A, plus momentum B, initial. So all of this is the initial momentum. If they have equal and opposite changes in momentum, that means that after the collision, momentum A, right, whatever its final momentum is, plus whatever its B's final momentum is, these are the same. The total is the same after and before the collision. If you were to literally calculate MA, VA initial, plus MB, VB initial, it's going to be the same as MA, V final, VA plus MB, VB, right? And then obviously velocity of direction. So it could be minus, right, if it's going left or right, depending. But the total momentum of the whole system of the A, like that's what I'm doing. I'm adding up momentum A plus momentum B. That's the whole system. Momentum of the system is going to initially is going to equal the momentum of the system final. We call this the conservation of momentum. Now, so conservation of momentum, pretty cool. That sounds like this universal law, like it governs everything. But the truth is, there's nasty things like friction, air resistance. The momentum is conserved when there are no outside forces. So, and that makes sense because change in momentum equals force net times time. If there's an outside force, there has to be a change in momentum. So for the whole system, if there's no outside force, then yes, we can say that the momentum initial equals the momentum final. So, yeah, this is kind of just the equation, right? If you have MA, VA initial, MB, VB initial, you can figure out, VA after the collision, right? Because you know the momentum is conserved, so you can actually use the momentum to figure out another variable after the collision, or before the collision. There's a few special kinds of these sort of collisions and interactions. The first one is, so your standard collision, right? Maybe they bounce away, maybe they bounce, but they still keep going the same direction. You can have all sorts of combinations with these, and I think we've seen this in the momentum unit. Another kind of thing is when they stick together. So you can have something where, like block A, and then block B is at rest, or maybe it's going very slow. Maybe there's like some Play-Doh or something, and then after the collision, they both kind of stick together. This is one of my favorite kinds of problems because it's kind of simple actually. Really, if you think about it, MA initial, MA plus VA initial plus MB VB initial is going to equal. Now you can, so here let's think about this. You could say MA V plus MBV, right? They have the same velocity though. Like when they stick together, they're moving together. We can factor out that V. We can say this is the same as V times MA plus B. And that sort of looks like you're doing, MA plus MB times V. It's sort of like you're treating this as one big object that's moving with a velocity. So it just kind of becomes M total times V, like your momentum total sort of, right? M total times V. So, right, if they stick together, you can once again mathematically determine what's the speed afterwards if you're given all the other information. So, yeah, pretty cool stuff. And then the final sort of thing is that, here, let me do this. Let's say you have a gun. You have a gun, and you're like a Nerf gun or something, so we're not violent. If you have a gun and then you shoot it, the initial momentum right before it is 0 for the whole system. I'm talking, because obviously the bullet's not moving, gun's not moving. And then after the collision, the bullet will be moving, but for the whole system, we know that momentum has to be conserved. In order for momentum to be conserved, if there is momentum this way, there has to be momentum pointing back. That's why the gun recoils and then moves back. And obviously it's not going to be moving as fast because it has such high mass. So if we think about the equation, momentum initial equals momentum final. The momentum initial is 0. It has to be 0, so the momentum final has to be 0. Because there's no outside forces on the gun bullet system. So we could say M gun times V minus, right, because they're opposite directions, minus M bullet times V, like bullet. And then you can add this on that side and then figure out what are their speeds based off their velocities, right? If this is actually 2 times more heavy, if you do the math, it'll be moving half as fast. So those are kind of the 3 main collision-y things that you gotta kind of have to remember. But also just, understand, right? There's no outside forces. You can determine, what kind of collision it could be. You can determine that momentum initial equals momentum final because forces cause changes in momentum. All right, I'm gonna talk about a few last things, small things, just things to remember, I guess. Bouncing, okay. A common misconception. So let's actually take a look at I don't know why I started whistling. I was thinking about what the scenario. I was like, oh yeah, I was gonna do that. So let's take a look at a wall. How much time are we at? Please don't be we don't be plus 30. It's gonna be, oh, it's right as I say that, it crosses the 30-minute mark. Okay, I'm gonna have to do time stamps or something. So this is kind of exhausting. So let's take a look at bouncing. If we have a wall, a common misconception is that when a ball bounces, right, into the wall and then bounces back with the same speed, people often think, and I used to actually think this all the time when I was myself, right, that momentum is conserved, right? Because the initial momentum of the whole system was m, whatever this m is, times v, right? And then the final momentum, well, it's same speed and same mass, it has to be the same, m times v. But remember, momentum has direction. And specifically in this case, if you're looking at the change in momentum of the ball only, it's going to be m v final minus v initial. And the v final is going to be, let's just say v. Let's say it's just v. And then we're going to subtract, but we're subtracting negative v. This velocity before the collision is negative. It's going the opposite direction. You have to do v minus negative v. And then the two negatives, right, that's the same as v plus v, or 2mv. So bouncing actually gives you more impulse, right, compared to like, starting from 0 and then going to speed, right? This is actually 2mv. There is a change in momentum, but then the wall doesn't move. So how can that happen? How can the ball have a change in momentum, but the wall doesn't? And the truth of that is that there's outside forces. There's support beams, there's friction, there's the building that are all providing all sorts of forces that will stop the wall from moving, right? If I do that, there's forces that will stop the wall from just falling or anything like that. So just remember, bouncing has larger change of momentum. If I have something that, let's say this bullet embeds into the thing and then they stick together, for this thing it'll be moving faster if the bullet bounces back, because then afterwards the ball has this small ball has a greater change of momentum because it changes direction. That's kind of the key thing. So this has to be moving faster for momentum to be conserved. So that's bouncing. The last small thing I'm going to talk about very briefly. I don't think. Like the main thing here is just understanding center of mass. So if two objects are sort of moving together, their center of mass, right, is going to be moving. So if I think about, like, maybe initially they have the same speed or something. If this is much more massive, you can imagine the center of mass is here, like right in between. The center of mass is also moving this way because the bigger thing is moving that way. But then after the collision, for the whole system, there's no outside F net. So the center of mass will actually be moving that same direction. Like the velocity of the center of mass isn't changing. So this shows up in a lot of ways. For example, if I took like a ball, right? Right now, the ball and my center of mass isn't moving. Right? Our center of mass is, I don't know, maybe somewhere here. When I throw it, I'm gonna, like, assuming there's no friction, the ball is gonna go that way. Equal opposite force is gonna cause me to go this way. Linear momentum is conserved. But our center of mass, where it originally was, it's staying in the exact same spot. It has no velocity. Our center of mass is not moving because initially our momentum was 0. So afterwards our momentum is, the total momentum is still 0 because they go in opposite directions, they cancel each other out. The velocity will also have to be 0. The way to figure out the velocity of the center of mass is that the total momentum of the system divided by the total mass of the system, right? That cancels out, and then you'll find out the velocity of the system. And that's why 0 momentum, like initially, will lead to 0 velocity for the system, like the center of mass. So yeah, that's not like that's just something to keep in mind, like something for like an explanation, right? Like what is the direction of the center of mass? Just remembering that kind of stuff. So if there is an F net, then yes, your velocity will change because change in momentum is caused by your change in momentum is caused by forces. So yeah, that was momentum. Sorry for the longer video. I didn't want to rush this one because I know the energy one was sloppy. So hopefully this kind of makes up for it. I'll try to do something for energy. But yeah, thank you for watching and have a good day. Good luck studying for those AP tests.